Okay, I mentioned before about autoencoder, but let me quickly tell you what autoencoder is. Autoencoder is basically, you can think of autoencoder as two networks that have been basically concatenated to each other. Think that this is your input in D dimension, and through, say for example, for simplicity, for a feed-forward. It could be another type of model, but say for example, it's feed-forward. Through a feed-forward or through a matrix P, D by P, it goes to another layer, and from P it comes back to D. Okay, so suppose that you only have these two layers. From D you go to P, from P you go to D. This is called autoencoder. So data goes through a bottleneck and come back to D. And what the goal is the goal is that you feed it with X and you want to reconstruct X. So the objective function is that X hat should be similar to X. Okay, this is autoencoder. If there is no nonlinearity, and if there is only one layer here, and no activation function, this model is sort of identical to PCA. It's as if you're applying PCA to data. When you apply PCA, through PCA you have d-dimensional points, and then you apply a transformation to this p-dimensional point and get y, which is in p dimension. Okay, so y now is in p dimension because this matrix is p by d. I mean, u is d by p, u transpose is p by d, and it gives you a new vector which is p by d. That's new representation of the data. So this would be your new representation of the data in p-dimensional space, and this is going to be your u transpose. Okay? And in PCA, actually, you can reconstruct points when you have u times y would be your x hat. Or basically, u transpose x would be your x hat. So if this is u transpose, that's going to be u. Okay? So this is basically very similar to what's happening in PCA. And in fact, the objective function has this form. If there's no nonlinearity, as if we are minimizing this and we are computing this u's. Okay? With the exception that in PCA you have an orthonormal constraint that u transpose u should be identity, and we don't have it here. So in a sense, it's not identical. It's not going to capture exactly the same basis as PCA, but it spans exactly the same space as PCA. Okay, the bases span the same spaces. So that's autoencoder, which is pretty old. Now you can make an autoencoder dip, and you can make it nonlinear. You may add nonlinearity to this layer, and you may add more layers here. Not just one layer, okay? Layers with nonlinearity. So that becomes deep autoencoder. So this is autoencoder. This is deep autoencoder when you have more layers and there are activation functions. We call this part of the model encoder, and we call this part of this portion of the model decoder. Okay? But encoder will map everything to some space Z. You can think of this Z as some hidden space that generate the data. And now I map everything back to this Z, and then I reconstruct. Okay, so autoencoder is quite simple, and there are different variations of that over complete autoencoder. For example, you may make this autoencoder over complete in a sense that when this is input and you want to reconstruct it, and this is in d-dimensional space, when you go to p-dimensional space, at the middle, p usually should be smaller than d, right? In overcomplete autoencoder, p is larger than d. So it goes to higher dimension and then come back. Yes?
What is the use of this and this?
The use of this is dimensionality reduction in general.
But then you're getting back x prime, which is the same dimension as x.
Yeah, but z is lower dimensional representation.
Z is the output.
Yeah. Z is lower dimensional representation.
And that?
Over complete autoencoder, you know, if I have like 10 nodes here and I have 20 nodes here, for example, and then I come back to 10 nodes. If you train it through gradient descent, you think what's going to happen? There's a trivial solution, and any wise optimization strategy is going to find this trivial solution. What is this trivial solution? Sorry?
Just x. The center one doesn't win.
This is 10, this is 20. So I can afford to exactly copy whatever I have here, and I don't care what the rest of these nodes are. So it has more than one solution, and then come back, right? So there's a trivial solution that copy x here, and then copy what you copied in the z back here. So it's useless, right? But what people does is to add some noise to the input. So you take away this trivial solution by adding some noise here. So the input is a little bit noisy. So if you just copy this here, you can't reconstruct x. Okay. So the input is noisy, the output is clean. Then it can be used as a method for noise reduction. You know, then you can, at the test time, you can point a point with low quality, which is noisy, and get a clean point out. So there are many different variations of autoencoder, but what we want to discuss today is variational autoencoder, which is quite different from this autoencoder in terms of math behind it. So variational autoencoder, in a sense, is marriage of graphical model and neural network. So that was the first paper. Since the first paper, variational autoencoder, many people try to have a model which has a graphical model and then turn this graphical model to a neural network with the same basically set up steps that people, the authors of variational autoencoder has taken that we are going to see. Variational autoencoder is based on variational inference. How many of you are familiar with variational inference? Okay, so I have to give an introduction to variational inference first, and then knowing about variational inference, we'll see how variational autoencoder is going to work. Maybe I just and if you want, turn on the light at the back. Okay, let me start with the concept of information. You can quantify information that a sentence or an expression, a statement carries by this expression. Information is defined as minus log probability of x when x is certain event. Okay? So probability is between 0 and 1. For values less than 1, the log would be negative. So it means that if probability is quite small, very small, then minus log of very small number would be a large number. And if probability is large, that's going to be a small. If probability is 1, it's going to be 0. Does it align with your intuition about information? You know, I have a sentence, and it's quite possible no information in it, or little amount of information. But I tell you something which is quite impossible, quite unlikely, and there's huge information. Does it align with your intuition or not? How? Can you explain? High probability, low information, low probability, high information.
Like if something happens which is of very low probability, then we are getting more information on it.
Yeah, but of course. But why? Give me an example. You know, if I tell you something which is trivial, tomorrow is going to be rainy or not rain. The probability of this event is 1, right? Because there's only 2 possibles. Either it's rain or it's not rain. So the probability of event is 1. But how much information did I give you? Nothing, you know. It's quite clear that tomorrow there's no any other choice, you know. It's going to be rain or not rain. No information, right? If I tell you that in July, the weather is going to be hot here. It's very likely. Not much information. But if I tell you in July, it's going to snow here. It's very unlikely, but lots of information in it, right? Because I'm talking about something which is very unlikely. Trump is unpredictable, you know. It's any sentence about Trump has huge information because you don't know what's going to happen. But Justin Trudeau is predictable. He's not in the news, right? You know what's going to happen in Canada because he's a predictable man. But Trump is not predictable. He's in the news every day, right? You don't know what he's going to decide tomorrow, what's going to happen. So if you want to be in the news, be unpredictable. Anyway, so that's information, right? We have another concept, which is basically the average of information. Okay, what is it called? Average of information? Entropy, right? So entropy basically is expectation of the information. That's entropy. Okay, now assume that I have 2 different distributions, P and Q. There is a concept which is closely related to the concept of information and the concept of entropy, which is called KL divergence. And KL divergence shows the dissimilarity between 2 different distributions. Okay, so KL divergence between distribution P and distribution Q is a measure of the similarity between these 2 distributions. And it is not quite right what I'm going to write here, but I will make the correction. But it is almost the entropy of P entropy of Q minus entropy of P. How much information do you have here minus how much information you have there? So if they are identical, they carry same information and vice versa. This is not quite right because KL divergence is always with respect to one distribution. So here basically I would say that KL divergence of Q with respect to P. And this with respect means that when you want to compute the average information, compute the average information with respect to P, not to Q. This is expectation, right? You can take expectation with respect to Q, or you can take expectation with respect to P. Take the average information always with respect to a single distribution, okay? So that's entropy, and you can simplify this as summation of Px, and this minus this is log of Px over Qx. That's the definition of entropy. Or some people prefer to write it as a negative Px log Qx over Px. There are two important things about KL divergence. One is that KL divergence is always greater than equals 0. And the other thing is then KL divergence is not symmetric. So KL divergence of P and Q is not the same as KL divergence of Q and P. They're different. So it's not distance. That's called, they call it divergence. Because distance should be symmetric. If distance between two distributions, one of the condition of a measure to be metric is to be symmetric. You know, distance from this city to other city is the same as that city to this city. But that's not true here. And to understand this concept, I mean, the intuition behind this concept, you know, this is a very good practice. You know, consider two distributions, P and Q, and suppose that they are discrete distributions exactly the same. 0.5, 0.5, 0.5, 0.5. Okay? Now, what would be KL divergence between P and Q? P is 0.5, Q is 0.5. So that's 1. The log would be 0, right? So summation over two possible points would be 0. So KL divergence is 0. These two are identical. And now make it different. You know, this is not 0.5 anymore. This is, say, 0.75. So this becomes 0.25. So this P is this distribution, but Q is the same. Now compute this. Now you have a log of 0.75 divided by 0.5. And then you have a log of 0.25 divided by 0.5. Compute that it's going to be a positive number, which shows that they are dissimilar. Okay? Okay, so KL divergence is a measure of the similarity between two distributions, but it's not the only one, but it has close connection to information and entropy, and people like it actually because these type of properties that it has. So now let's get back to a graphical model that I told you. Variational technique is a technique for inference in graphical model. So suppose that I have Z and I have X. X is my observation and Z is my hidden variable. Okay? And I would like to compute posterior, Pz given X. pz given x actually is going to be px given z times pz divided by px, or pxz divided by px. Computing this px is quite complicated because this is a marginal distribution which is basically integral of px given z times pz dz. And if, this integral could be intractable, and it is intractable in many cases. We don't know how to compute this integral. Especially in high dimensional space, if z is high dimensional, then this integral has this form. So this is one of the main obstacles in graphical models, that computing this marginal is intractable. We don't know how to deal with this. So roughly there are two main approaches to handle this. One of them is Monte Carlo approach. So I can compute this integral using Monte Carlo integral, for example, right? I can sample. I can do Gibbs sampling. I can do Metropolis Hastings. I can sample and compute. That's one approach. Another approach is variational inference. Okay. If you want to compare these two, basically one of them is unbiased with high variance, like when you sample. And the other one is low variance or zero variance, like variational inference. It could be exact, but it's biased estimator. But it doesn't matter for the moment. So one technique is based on Monte Carlo. The other technique is based on variational inference. So what is variational inference? Variational inference is that I want to compute pz given x. I can't. Okay? Okay, let's approximate p z given x by another distribution. If I choose Q to be a tractable distribution, say in the family of Gaussian exponential, so it's a tractable distribution, then I play with the parameter of distribution in a way that distribution is close enough to this one. Then I have an approximation of a distribution that I can't compute. So basically, I go around this problem, by jumping from this to a distribution that I know how to deal with. I choose a tractable distribution. I try to make this tractable distribution as much possible to this one. Okay, then my problem is solved. Okay, that's the idea. Okay, so I want to make Q similar to P, and this Q actually could be, Q, you can choose Q such that it depends on X or independent on X. It depends on how you interpret this problem, I can say X is given, so I just need to know the density at point Z, so it doesn't matter, just give me QZ. Or I can say that, okay, no, it's a dependent distribution. For the moment, it doesn't matter. So I want to make Q as close as possible to P, right? So the measure that we just talked about, KL divergence, could be helpful. So let's make Q close to P. So let's minimize KL divergence. If I can minimize KL divergence, then I have a Q which is similar to P. Yes?
Why not write it KL of P with respect to Q?
So you can. But as I told you, it's not symmetric.
It's not symmetric, so how do we build an intuition of which one is correct if KL divergence is aiming to make P?
Let me finish this and then I give you two examples of the, in terms of geometry, not in terms of probability. It's much easier to see the difference between these two. In terms of geometry, it's as if you're basically you're preserving local information, local distances with respect to one point, rather than global. Well, I give you an example to show you the difference. Okay, so I want to minimize the KL divergence, okay? Based on definition of KL divergence, so this is Qx log P over Q, right? But in fact, I wanted actually to make QZ similar to PZ given X. So this is my QZ. And this is PZ given X. Okay. PZ given X is PX given Z times PZ divided by PX, or it is PX and Z divided by PX. Let's replace this for PZ given X. So I substitute this here. So my KL divergence between these two quantities that I would like to minimize is QZ log PZ given X, which is PX and Z divided by PX QZ. So this is minus QZ log PXZ divided by QZ times PZ, right? Times PX, sorry. Okay, is that okay so far? Okay, so I write it as minus log QZ log PXZ QZ. This is a log of product. I can write it as sum of logs, right? So plus log 1 over px. Or this log over 1 px, I can write it as minus log px. So it is minus qz log pxz over qz minus or plus qz log px. Is that okay so far? Okay, this summation is over z. And log px has nothing to do with this. I can take it out, right? So here I can write this one as log px summation over z of qz. What is summation over z of qz? 1, right? So this is 1. So my KL divergence is this term plus log of px. So I can write it as log of px is equal to KL divergence between qz and pz given x plus this term. Right? Okay. You know, x is given. If I give you x, log of px is a fixed number, no matter what the q is, right? If I change q, if I change the parameters of q, it doesn't matter. This is a fixed number. That was the number, that was the quantity that I wanted to minimize in the first place. Now I realized that a constant equal to the quantity that I wanted to minimize plus another quantity. Let me call this quantity L. So L plus KL divergence is equal to a constant. And I want to minimize KL divergence. So instead of minimizing KL divergence, I can maximize L, right? Because the summation is a constant. This L is called variational lower bound. In variational inference, usually we deal with this one, with maximizing lower bound. Why is it called variational? Well, is it called lower bound? Because KL divergence is always greater than or equal to 0, right? So, and log of px is equal to this 2 quantity, and this is positive. So I can say this L is always less than. I can say L is less than equal log of px. So this is a lower bound of log probability. And if you maximize lower bound of another function, you know, suppose this is lower bound of this function, and I try to maximize it. So I push this up, and this is lower bound of this. So this should go up as well, right? There's no way out. So if you maximize a lower bound of a function, you're maximizing that function. I mean, if a function is lower bound of another function, you're maximizing this. They have this shared same parameters. So basically, you're maximizing the other one because that should be always larger than this. Okay. So this is called variational lower bound, and you know, in like conventional mean field variational inference, what people do actually is to assume that Q has a tractable form, and it's usually they assume that it's you know, basically you can write QZ as QZ1 times QZ2 times QZ3. Basically on each dimension it's independent, and then it leads to some sort of other simplification. They can solve the problem, which is out of the scope of our course now. It's a mean field variation. But look at this lower bound. So lower bound is QZ log Px and Z divided by QZ. Okay. Okay, let me write this P, X, and Z as P, Z given X times PX. So this is the same as QZ log PZ given X times PX divided by QZ. So this is QZ log P Z given X plus log PX QZ. Right? Okay, this is QZ log PZ given X plus QZ log PX QZ. What is this quantity? KL between KL between Q and P. Negative, right? So this is negative KL between Q, Z, and P, X. Or did I? Sorry? Did I make any mistake? This is PZ given X. Times PX, so X given Z. And what is this term? This is expectation of log PZ given X with respect to Q. Right? Yes.
You want to write it backwards? Sorry, when you on line 2, when you wrote P of X comma Z as P of Z given X times P of X, should that not be backwards?
Yes. Yeah, we had problem with Z given X right from the beginning. So it's Px given Z times Pz. So this is Px given Z times Pz. This is P x given Z. This is Pz. This is Pz. Yeah, thank you very much. Because right from the beginning, I mean, you can write it as Pz given X times Px. But we had problem with Pz given X. We started everything because we were not able to compute Pz given X. If we can compute it, it's the end of the story. We need to go through these troubles. So let's write it as Px given Z times Pz instead of Pz given X times Px. So that's going to be KL divergence between Qz and Pz. And what would be the first term? Yes?
The entropy of the conditional distribution.
Right. Also, it's expectation of this conditional distribution, right? So that's expectation of P x given Z with respect to Qz. So, and that was, if you remember, that was my lower bound. So lower bound can be written in this form. And also can be written, a lower bound can be written as this form. Expectation with respect to QZ, P x given Z plus or minus KL divergence of QZ PZ. Right? Okay. So
That should be expectation of log of P.
log of what?
The last one, expectation of the log.
Of log, yes. Thanks. Expectation of this log. So basically, to make Q similar to P, I can minimize KL divergence. It's identical to maximize lower bound. And lower bound means that make your Q similar to P. Okay. Meanwhile, maximize the expectation. I mean, given Z, you observe some X's, maximize this basically the likelihood of observing these points. Okay, means that should generate actually your observation. Okay, so now let's look at this lower bound and see how come this can be turned to an autoencoder. So I have this graphical model, and this is P x given Z. Let me assume that there is another distribution here, which is Q, which maps X to Z. Pz given X is hard to compute. I want to compute Qz given X to be similar to Pz given X, which was hard. And I write the KL divergence, and I come up with this lower bound, which I have to maximize. In this form, I have a Q which maps X to Z. And I have a P which maps Z to X. Okay, and Z is my hidden code or hidden variable. Okay, I'm going to assume that this Q is a neural network because Q is a function, right? Q is a function which maps X to Z. I'm going to assume that this Q is a neural network which takes input X and map it to Z. And then I'm going to assume that my P is another neural network which takes Z and map it to X. Okay, now this is variational bound for this model if I want to treat these two as two probability. Okay, so what does variational bound tell me? The variational bound told me that I can add more restriction actually to my model. It told me that the KL divergence between what you observe here, to have no confusion basically, you can assume that this is Pz given X. What you observe here, the distribution of this should match another distribution P, and you're going to choose what that distribution is. I told you that you can go to a tractable family, for example. I'm going to assume that I want this Z to have Gaussian distribution, for example. Okay, so I have an autoencoder, a part of my cost function, which tell me that make the distribution of this hidden space similar to a distribution that you're going to choose. And I'm going to choose Gaussian. So make distribution of Z Gaussian. What this part of the objective function will tell me. This part of the objective function is conceptually reconstruction error. Why? Because, when I'm talking about Px given Z, from Z to X, I have a neural network. Let's call it X hat. From Z to X hat, I have a neural network, right? It's completely deterministic. It's not probabilistic. It's completely. So if I give a Z here, I will observe X hat here. If I repeat this process 10 times, I will observe the same X hat here. So it's completely deterministic. So we can think of Px given Z as Px given X tilde, because there's a deterministic function between Z and X hat. Now, imagine that this distribution have a Gaussian form. It could have different forms, but if it has a Gaussian form, for example, then it has a term of this form. And if you take a log of this, you're going to have this form. So basically, when you're maximizing this, if the distribution of your X is Gaussian, it's as if you're minimizing the reconstruction error. Now, instead of Gaussian, assume that this is Bernoulli, for example, and write it down. It's going to be similar to cross entropy instead of this type of L2 loss. It's going to be cross entropy. So this term acts as sort of reconstruction error. And this term will tell you that the distribution of Z should be similar to something that you're going to choose. Right? So now the story is clear. I have an autoencoder. The autoencoder cost function traditionally was this. Minimize this. So we want to minimize this, but not only this, you want to minimize the distance between what you're going to observe here and a noun distribution. And this noun distribution could be a Gaussian. So it's as if you have an autoencoder and you add a regularizer to this autoencoder, which makes sure that this distribution has a certain form. Okay? But don't forget that we have a graphical model, and these are random variables. And the form that I explained so far, everything seems to be completely deterministic, where this non-deterministic part comes to play. In fact, when we are talking about this distribution, being close to this distribution, you have to design your network in a way that it doesn't generate the code of Z. It generates the parameter of the distribution, which generates Z. So Z is normal. So Z as a normal distribution has two parameters, has mu and has sigma. Multivariate distribution, right? This mu is d-dimensional vector. This sigma is d by d. For simplicity, let's assume that it's diagonal. So it's sort of, diagonal. So everything else is 0 except everything that you have on diagonal. So in this case, this is also going to be D. Right? You can assume it's not diagonal, but for simplicity, assume it's diagonal. So make this part mu and this part sigma. So this is D and this is D. So force the network or train the network to generate the mean of this distribution and the variance of this distribution. Now you have mean and you have the variance of a distribution. Now sample from this distribution and then pass the sample to this part. Sample from this distribution, this is your Z now, and generate X. So if you sample 100 times, you sample 100 different points here. You generate 100 different points here, right? Something interesting actually here is that you can use this model as a generative model. In which sense? I have this autoencoder. I give X and I generate X, right? So the training is done. Z is Gaussian with some mu and covariance. Okay. Now, forget about your encoder. You have a Z and you know the parameters of your Z, mu and sigma. Sample from this Z and feed it to this network. Intuitively, what's going to happen? All X's are mapped in a hidden space with a certain distribution. And now you are sampling from that distribution, fit to decoder. What's going to happen? It should generate points similar to points that you have observed. You can think of this as, okay, my observation is MNIST, handwritten digits. Distribution is quite complicated. I have a transformation here which change this distribution to Gaussian distribution, which I can handle. I know how to sample, and then I have another transformation which take one of these points of this distribution of Gaussian and give me something similar to MNIST, handwritten digits. Now I don't need this part. I sample from the Gaussian and fit to this part. I have the transformation to transform a Gaussian point to MNIST point, right? So it should be a generative model now. I can sample from Z and generate something that I haven't observed now, a new point. And it does work, in fact, this way. Let me show you. Where did I put? This is when you sample from this Z and feed it to this network, and you generate some points. It looks like it has been trained on MNIST. It looks like handwritten digits. But these handwritten digits are not among the points that you observed in your training set. They are new. And you can do it with face. You can do it with any other object, Basically map everything to the space of Gaussian and then generate from Gaussian to come back to, something that you haven't observed before. And it also quite interesting in terms of the manifold that it finds because, say, for example, it's a low-dimensional Gaussian. You know the structure of that, right? Who is similar to whom, who is far apart from that. And then you can sample from a grid there and then regenerate them. And then you're going to see a grid like this, for example, which is a pretty interesting pattern. You know, the 7 is really similar to this 9. And with some smooth way, it goes to 1, you know. Everything is quite smooth here, you know, between basically morphing between images goes through very smooth, yes.
So for this, you train the input, the encoder part of it using MNIST images, just MNIST data, right? Single images of single digits. Each input that is being used to train is just a single digit of the MNIST digit, single picture of the MNIST digit, correct?
Yeah, but you train it with the whole MNIST, not with a single image. I mean,
yeah,
right.
the entire thing. But each time we just feed only one image.
Yeah.
And this output is obtained after dimensionality reduction using that. And so to trigger the output using that, as it's already learned the weights in between those two layers, right? So two questions. Firstly, is this generation of many digits, could you explain how this output is obtained from, say, like what is it trying to output? Is it outputting outputting a collection of MNIST digits, right?
No,
One digit?
you know, if I sample 1 point from Z, only 1 point, and feed it to this network, it gives me 1 digit only. Okay, another sample give me another digit. But if on Z I make a grid, and from this grid, let me give you a simpler example. You know, forget about this. Suppose that I do PCA, okay? And in PCA, I have MNIST, I have 7, 1, whatever. And through MNIST, I map everything to, through PCA, I map everything to 2-dimensional space, okay? So every point in this 2-dimensional space is 1 image, right? So if I take this point, and if I compute U transpose this point, it's going to give me an X, which is 110 digit, right? Now, if I make a grid here, or even simpler than a grid. So this is, suppose that this is 1, and this is 5. I make a line between these, and try to reconstruct every single point on this line. So the first point should be 1, the last point should be 5, and whatever is in between should be some sort of a smooth transformation from 1 to 5, as if I'm morphing 1 to 5, okay? Or if I have a grid here, and if I choose those points and reconstruct them through PCA. So that's I mean, if you do this experiment with PCA and MNIST, it's not going to happen this way because, you know, it's just linear. You know, you don't have a good way of reconstruction. But here, actually, it's a nonlinear, very complicated transformation that can handle this type of complicated objects.
So while PCA, you have mapped an MNIST image of a digit onto a 2D space, right?
For example, that was just an example.
That was just only PCA.
Yeah, this 2-dimensional space is your Z here. But Z here actually has a structure, additional structure, which is being Gaussian. And whenever you sample from that Gaussian, you are on that manifold, you know. You are on that manifold. And you generate something. Otherwise, you know, if it's like, say it's 2-dimensional, and I don't have this restriction, and I choose a point in 2-dimensional, it's not necessarily corresponding to 110 digits, you know. When it goes through this decoder, you know, it may look like something which is not an image, 110 digits. What guarantees this to be 110 digits is that we put a restriction here that everything will be mapped to a Gaussian. Everything in this Gaussian is on that manifold, you know, and will come back to 110 digit, or face, or whatever. Yes?
Would this output look very different if we choose another distribution?
What do you mean?
If we chose Bernoulli instead of Gaussian,
If you choose?
any other distribution like Bernoulli.
Yeah, I don't know, but you know, one good reason actually to choose Gaussian is that if this is Gaussian, the KL divergence has closed form. You know, when you want to compute, when you want to really implement this, and you want to minimize the KL divergence between two distributions, if you assume that this Gaussian is a non-Gaussian and this one is a Gaussian, then KL divergence between these two has a closed form that you can take derivative and solve. You know, in general form, this lower bound is not easy to maximize. You know, in a most general form, this lower bound is not easy to maximize. There are many techniques actually in variational inference which basically talks about how to maximize the lower bound. You know, in min field, you know, there's that assumption of independence which make the problem simple, and assuming that Q has some sort of a structure. But in general, when you don't make this type of assumption, it's not an easy problem to solve. One thing that makes it easy here is this assumption that it's Gaussian. If you assume that it's something else like Bernoulli, it's not going to be hard. It's tractable again, I think. But in terms of result, I'm not sure actually what would be the result. I haven't tried that. Okay, so any other question? Or maybe no any other question, because we are over time and the next class will start here in 5 minutes. I can answer questions offline.